Fuses are primarily designed for short-circuit protection, where there is a high current flowing due to a fault, whether it is phase-to-phase or phase-to-neutral. Fuses operate by melting a fusible element and interrupting the current flow. In a ground fault that is phase-to-ground, the behavior of a fuse depends on several factors. Firstly, fault resistance is important because if there is a high resistance in the ground fault path, for example due to soil resistance, the current may not be high enough to exceed the fuse rating. This is especially true for higher voltage systems, where the fault current may be limited. Secondly, fuse speed is crucial. Fuses have different speeds, which determine their response time to overcurrents. Fast fuses blow quickly, while slow fuses take longer to react. In cases of low fault current, a slow fuse may not blow even with a solid ground fault. Fuses are not typically used for ground fault protection alone. Ground fault protection is usually provided by ground fault interrupters, also called GFI, or ground fault circuit interrupters, known as GFCIs. Consider transformer configuration. In a delta-connected transformer, the phase currents do not sum to zero. Therefore, a ground fault in a delta system may result in circulating currents that do not pass through the fuse. However, in a Y-connected transformer, the phase currents sum to zero. A ground fault in a Y system will cause a current to flow through the fuse, tripping it open. To summarize, while fuses are primarily for short-circuit protection, they can also provide some limited ground fault protection in certain situations. However, the factors discussed, such as fault resistance, fuse speed, and transformer configuration, can affect their effectiveness in ground fault protection. It is important to provide dedicated ground fault protection devices, such as GFI or GFCIs, for complete safety. It is important to elaborate on the factors that influence fuse behavior in ground fault scenarios, going into more detail to ensure a comprehensive understanding. Let's begin with fault resistance. The resistance of the ground fault path plays a pivotal role in determining the magnitude of current that will flow during a ground fault. A high-resistance ground fault path impedes the flow of current, potentially limiting it to a level below the fuse's tripping threshold. Several factors contribute to ground fault path resistance. Soil resistance, particularly in outdoor installations where grounding electrodes are employed, can significantly impact the fault current. Dry or poorly compacted soil exhibits higher resistance than moist, well-compacted soil. The length and gauge of grounding conductors also influence the resistance of the ground fault path. Longer conductors and those with smaller cross-sectional areas present higher resistance to current flow. Connections within the grounding system, such as those at grounding electrodes, equipment grounding terminals, and bonding jumpers, must be properly made and maintained to minimize resistance. Corrosion or loose connections can increase resistance, thereby reducing fault current. Consider the type of grounding system utilized. Solidly grounded systems offer a low impedance path for ground fault currents, whereas impedance grounded systems intentionally introduce resistance to limit fault current. The level of resistance in an impedance grounded system directly affects the magnitude of ground fault current. In higher voltage systems, the impedance of the grounding transformer or neutral grounding resistor can significantly influence fault current levels. Next, consider fuse speed. The time current characteristic of a fuse determines its response to overcurrent conditions, including ground faults. Fuses are available in a variety of time current characteristics, each designed for specific applications and protection requirements. Fast-acting fuses, also known as general-purpose fuses, are designed to quickly interrupt overcurrents, providing rapid protection against short circuits and ground faults. These fuses are suitable for applications where immediate fault clearing is essential to prevent damage to equipment or wiring. Time delay fuses, also referred to as slow-blow fuses, incorporate a built-in time delay that allows them to withstand temporary overloads without tripping. These fuses are commonly used in motor circuits and other applications where brief inrush currents are expected during startup. Current-limiting fuses are designed to rapidly interrupt high fault currents, limiting the let-through energy and minimizing damage to downstream components. These fuses are particularly effective in protecting sensitive electronic equipment and reducing the risk of arc flash hazards. The selection of fuse speed should be based on a careful evaluation of the application's specific requirements, including the potential for overloads, the sensitivity of protected equipment, and the desired level of coordination with other protective devices. A fuse that is too fast may trip unnecessarily due to harmless transient overcurrents, while a fuse that is too slow may not provide adequate protection against ground faults. Next, let us consider ground fault protection. While fuses can provide a degree of ground fault protection, they are not specifically designed for this purpose. Dedicated ground fault protection devices, such as ground fault circuit interrupters and ground fault relays, offer superior sensitivity and response to ground faults, enhancing safety and reducing the risk of electrical hazards. GFCI devices are designed to detect imbalances in current between the hot and neutral conductors in a circuit. If a ground fault occurs, a portion of the current will flow through an unintended path, such as a person's body, creating an imbalance that the GFCI detects. When the imbalance exceeds a predetermined threshold, typically 5 mA, the GFCI trips, interrupting the circuit and preventing electrical shock. GFCIs are commonly installed in areas where electrical equipment may come into contact with water, such as bathrooms, kitchens, and outdoor locations. Ground fault relays are used in industrial and commercial power systems to provide ground fault protection for equipment and circuits. These relays monitor the current flowing in the grounding conductor and trip the circuit breaker if the current exceeds a set point, indicating a ground fault. Ground fault relays offer adjustable sensitivity and time delay settings, allowing for customized protection based on the specific requirements of the application. Coordination studies are often performed to ensure that ground fault relays coordinate properly with other protective devices in the system, minimizing nuisance tripping and maximizing system reliability. Now consider transformer configuration. The configuration of a transformer's windings, whether delta or Y connected, significantly influences the behavior of ground fault currents in the system. In a delta-connected transformer, the phase windings are connected in a closed loop, forming a triangle shape. This configuration does not provide a direct path for ground fault currents to return to the source, as the phase currents do not sum to zero. As a result, ground faults in delta systems can be more challenging to detect and clear than in Y systems. In some cases, ground faults in delta systems may result in circulating currents that do not pass through the fuses, making it difficult for the fuses to trip and clear the fault. This can lead to prolonged fault duration and increased risk of damage to equipment. To address this issue, delta systems often employ impedance grounding techniques, such as using a grounding transformer or a neutral grounding resistor to provide a path for ground fault currents and limit their magnitude. In a Y-connected transformer, the phase windings are connected in a star shape with a common neutral point. This configuration provides a direct path for ground fault currents to return to the source, as the phase currents sum to zero at the neutral point. As a result, ground faults in Y systems are generally easier to detect and clear than in delta systems. When a ground fault occurs in a Y system, the fault current flows through the grounding conductor back to the neutral point, tripping the fuse or circuit breaker and interrupting the circuit. The magnitude of the ground fault current is determined by the impedance of the grounding path, which includes the grounding conductor, the grounding electrode, and any intentional impedance added to the system. Finally, consider other factors. Other factors can also influence the effectiveness of fuses in ground fault protection. These include the voltage level of the system, the available fault current, and the presence of other protective devices. In higher voltage systems, the impedance of the wiring and equipment can limit the magnitude of ground fault currents, making it more difficult for fuses to trip and clear the fault. In such cases, dedicated ground fault protection devices may be necessary to provide adequate protection. The available fault current at the point of the fault also affects the ability of fuses to clear ground faults. If the available fault current is too low, the fuse may not trip quickly enough to prevent damage to equipment or injury to personnel. Coordination with other protective devices, such as circuit breakers and ground fault relays, is essential to ensure that ground faults are cleared quickly and effectively. Coordination studies should be performed to determine the optimal settings for each protective device, minimizing nuisance tripping and maximizing system reliability. To recap, fuses are primarily designed for short-circuit protection, but they can also provide some limited ground fault protection in certain situations. However, the effectiveness of fuses in ground fault protection depends on several factors, including fault resistance, fuse speed, transformer configuration, and other system parameters. Dedicated ground fault protection devices, such as GFCIs and ground fault relays, offer superior sensitivity and response to ground faults, enhancing safety and reducing the risk of electrical hazards. A deeper understanding of these principles is essential for electrical professionals, leading to safer and more reliable electrical systems. To further understand the nuances of fuse behavior in ground fault scenarios, let's consider specific examples and practical applications. Imagine a scenario in an industrial facility where a 480 volts, three-phase, Y-connected power distribution system is in place. The system incorporates fuses for overcurrent protection, but lacks dedicated ground fault protection. A ground fault occurs when a phase conductor comes into contact with the metal enclosure of a motor. The resistance of the fault path is relatively low due to the solid connection between the conductor and the enclosure. However, the grounding conductor connecting the motor enclosure to the system ground has a slightly elevated resistance due to corrosion at a connection point. In this scenario, the magnitude of the ground fault current will depend on the system voltage, the fault path resistance, and the impedance of the transformer. If the fault current exceeds the tripping threshold of the fuse protecting the motor circuit, the fuse will eventually blow, interrupting the circuit and clearing the fault. However, if the fault current is below the fuse's tripping threshold, or if the fuse is a slow blow type, the fault may persist for an extended period, potentially causing damage to the motor and creating a safety hazard. Now, let's consider a different scenario involving a 208 volts, three-phase, delta-connected power system in a commercial building. In this system, a ground fault occurs when a phase conductor comes into contact with a grounded metal conduit. The absence of a neutral conductor in the delta system means that there is no direct path for ground fault current to return to the source. As a result, the ground fault current may circulate through the system, potentially causing voltage imbalances and equipment malfunction. In this case, the fuses may not trip, even if the ground fault current is significant, because the circulating current does not pass directly through the fuse elements. To address this issue, the delta system may be equipped with a ground fault detection system that monitors the system for ground fault currents and provides an alarm or trip signal when a fault is detected. Alternatively, an impedance grounding technique, such as a zigzag transformer, may be employed to create a path for ground fault currents and limit their magnitude. Now consider a residential setting with 120 volt circuits protected by standard circuit breakers. A ground fault occurs when a damaged appliance cord exposes a live wire that comes into contact with the metal case of the appliance. If the appliance is plugged into a GFCI protected outlet, the GFCI will quickly detect the imbalance in current and trip, interrupting the circuit and preventing electrical shock. However, if the appliance is plugged into a non-GFCI protected outlet, the ground fault current may flow through the person's body if they touch the appliance, resulting in a potentially fatal electric shock. This scenario highlights the importance of GFCI protection in areas where electrical equipment may come into contact with water or other conductive surfaces. Another practical application of ground fault protection involves the use of ground fault relays in industrial power systems. Ground fault relays are designed to monitor the current flowing in the grounding conductor and trip the circuit breaker if the current exceeds a set point, indicating a ground fault. These relays are often used to protect critical equipment, such as motors, generators, and transformers, from damage due to ground faults. Ground fault relays offer adjustable sensitivity and time delay settings, allowing for customized protection based on the specific requirements of the application. For example, in a motor circuit, the ground fault relay may be set to trip quickly in response to a high-magnitude ground fault current, preventing damage to the motor windings. In a transformer circuit, the ground fault relay may be set with a longer time delay to allow for temporary inrush currents during transformer energization. Coordination studies are often performed to ensure that ground fault relays coordinate properly with other protective devices in the system, minimizing nuisance tripping and maximizing system reliability. These examples illustrate the importance of understanding the factors that influence fuse behavior in ground fault scenarios and the need for dedicated ground fault protection devices to enhance safety and prevent equipment damage. By implementing appropriate ground fault protection measures, electrical professionals can create safer and more reliable electrical systems in a variety of applications. Furthermore, delving into the NEC, that is, National Electrical Code, provides specific guidance on ground fault protection requirements. NEC Section 230.95 addresses ground fault protection of equipment for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 1000 volts phase to phase for each service disconnecting means rated 1000 amps or more. This section mandates the installation of ground fault protection to minimize damage to electrical equipment. The maximum setting of the ground fault protection shall be 1200 amps and the maximum time delay shall be 1 second for ground fault currents equal to or greater than 3000 amps. The purpose of this requirement is to provide a higher level of protection for electrical equipment against ground faults, reducing the likelihood of damage and downtime. NEC Section 215.10 covers ground fault protection for feeders. Each feeder disconnecting means required to be readily accessible shall be provided with ground fault protection of equipment where the disconnecting means is rated 1000 amps or more and is supplied by a solidly grounded wire electrical system of more than 150 volts to ground, but not exceeding 1000 volts phase to phase. This requirement is similar to that for service equipment and aims to protect feeders from ground fault damage. Exceptions to this rule may apply in certain industrial installations where qualified personnel are continuously available to oversee the electrical system. NEC Section 517.17 addresses ground fault protection in healthcare facilities. This section requires ground fault protection for essential electrical systems in hospitals and other healthcare facilities to ensure the continuous operation of critical equipment during power outages or ground fault conditions. The requirements for ground fault protection in healthcare facilities are more stringent than those for general electrical systems due to the sensitive nature of the equipment and the potential for life safety issues. The NEC provides detailed guidelines for the design, installation, and maintenance of electrical systems, including specific requirements for ground fault protection in various applications. It is essential for electrical professionals to be familiar with the NEC requirements and to follow them carefully to ensure the safety and reliability of electrical systems.